Welcome back, guys. I'm going to quickly go through what I did on the previous presentation, and then we'll try to solve it in problems. So what I'm saying is that mg is going straight down, and it's made up of two components. One that's opposite the normal, one that's opposite the incline. And I'm saying this one that's opposite the normal is equal to mg cosine of theta, and this one is equal to mg sine of theta, where theta is always this lower angle. So I'm going to show you again why this is true, because this is often a place where people get confused. Again, I'm going to drop mg down, and with the ground, this is going to make a 90-degree angle. And so that tells me that this angle plus that angle plus that angle has to equal 180 degrees. So that would be 90 plus theta plus blank is equal to 180 degrees. So that would mean that blank is equal to 90 degrees minus theta, which is this angle in here. This angle, or this vector that comes off of here, our component, is perpendicular to the surface because it's opposite the normal. So that means that this is a 90-degree angle. This unknown angle in here, which we want to find out, we don't know, but we know this angle plus that angle plus that angle will be equal to 180 because it's a line. So I'm going to have 90 plus blank plus 90 minus theta is equal to 180 degrees. To make this true, this unknown needs to be theta. And that's why this is mg sine of theta, because it's the opposite side. This is mg cosine of theta, because it's the adjacent side. All right, let's solve a problem. So again, they're showing us that these are the same angles. This is not an FBD. As soon as you put components on it, it is definitely not an FBD, and this arrow is way too long. Again, not an FBD, but the one opposite normal is mg cosine theta. The one that's going down the incline is mg sine of theta. All right, a 10-kilogram block is stationary on an incline of 30 degrees. Find F, fric, and N. So our picture is a block. When they give you the angle, it's always the angle with level. Why is that? Because we consider 0 degrees to be flat, and anything up from that is how we talk about inclines. So I'm going to choose a dot that I can do my free body diagram from. And I'm going to say that weight is going straight down. Normal is going at an angle. And friction is going up the incline. So it's keeping it from sliding down the incline. To solve these, I'm going to pick this up, take it off of the smartboard, rotate it, and put it back down. And so I'm going to have it so that the normal is straight up. The friction is sideways, and the only thing that's at an angle is mg. So I twisted it this way. And now, instead of having an x and a y axis, the two directions that I'm going to consider is perpendicular to the incline and down the incline, or parallel to the incline. So mg is at an angle. I'm going to take this off, even though this is not a free body diagram. As soon as I rotate it, I changed it. It was not representative of the directions anymore. And I'm going to draw my components and my theta which is 30 degrees. So this side is the adjacent side. So when you use cosine, this side is going to be mg cosine of 30 degrees. This side is going to be the opposite. This is going to be mg sine of 30 degrees. And you need to use the degree symbol. If you just write down mg cosine of 30, that is in radians, that is not in degrees. All right, now I can use them to find out friction and normal. So I'm going to say that perpendicular to the incline, fnet is equal to 0. I recognize the situation I'm in. The forces are balanced perpendicular to the incline. So I'm going to take, from here, my ups minus my downs. So this is going to be n minus mg cosine 30 is equal to 0. So the normal is being balanced by this part of the weight. So I'm going to add mg cosine of 30 to the other side. And I'm going to find out that this is 10, 10. And again, we're not putting the negative in because the negative was direction. And we already did that. We subtracted that. And this is going to give us 87. Then I'm going to say parallel to the incline. Fnet is also at 0. It's not moving. It's not moving up or down. So it is balanced at rest in both of our chosen axes. So I'm going to take rights minus lefts in this case. Going to the right, I have mg sine of 30. Going to the left, I have the force of friction. So I'm going to add the force of friction to the other side, and I get that mg sine of 30 is equal to friction. So plugging in what we have, I have 10 kilograms, 10 meters per second squared. And so friction is equal to 50. All right, as far as we're concerned in here, the role of a pulley right now is just to change direction. So for us, pulleys, string are both massless, and pulleys are frictionless. And I'll show you super pulleys very soon in a lab. So if this is 100 pounds, no matter where I am on this rope, there's 100 pounds on it. All right, so we're going to flip this a little bit, and we're going to hang a weight off of an incline. So I'm going to have an incline that I don't know what it is, but it's frictionless. And I'm going to have a 2 kilogram weight connected by a rope to a 0.5 kilogram. And I don't know what this is. So I'd like to know what the angle of my incline is. I'm going to have 2 free body diagrams. For the 0.2 kilogram block, my free body diagram is going to be tension up and M1G down. And those should be the same because we're in equilibrium. Try to do a better job to draw it to scale. So again, this is for the 0.2 kilogram. We're going to have tension up. Still feel like that's a little bit long. But M1G down. So this is at rest. This is fnet equals 0. And I'm going to have T minus M1G equals 0. So T is going to be equal to M1G. And this is going to be equal to 0.2 kilograms times 10, or 2 newtons. For the 0.5 kilogram block, I have tension going at an angle. We're going to have normal going perpendicular to our incline, and we're going to have weight going straight down. And I'm just calling it M2 because it's the second one that I encountered. Now that I'm done with this free body diagram, I can pick it up and spin it. And I'll spin it so that our tension is sideways, our normal is up, and M2G is at an angle. And this angle theta that I want is this angle here. Then I'm going to rewrite M2G this is going to be M2G sine of theta, because it's the opposite side. And now, if I consider my parallel to the incline, I have fnet equals 0. I'm going to take right minus left. Going to the right, I have M2G sine of theta. Going to the left, I have T. So I'm going to add T to the other side. I'm going to divide by M2G. And I'm going to take the sine inverse of both sides. So this is going to be the sine inverse of the tension we solved with our first free body diagram, which is 2, because same rope, same tension. And M2G is going to be 0.5 times 10, which would be 5 newtons. Making sure my calculator is in degrees, I'm going to take the sine inverse of 2 divided by 5, which I got 23.57. I'm just going to say that it's 24. So same problem, a little bit different of what they're going to ask you. And we'll do a lab where we do this for 3 consecutive angles.